Thank you very much and welcome to everyone to this web seminar. It is, of course, my pleasure to introduce to all of you, if you don't know yet, Bernold Fiedler from Freie Universität, Berlin, and is going to talk about one of our favorite subjects, reaction, diffusion, and advection in one space dimension, but just an introduction. Please.
Well, thanks a lot. One of our favorite subjects means his and mine, okay? But I will not talk to him, okay? So co-authors, I don't talk to him. So let me first mention some of the people who were involved, and there's Pablo Castañeda is co-author, Juliette Hell, Filippo Lapissi, who is here, Brian Smith, and then Carlos Rocha. So he is the default co-author, at least in this talk, okay? He is the default co-author, so if I don't mention, it's him. And then I mention some contributions by other people, and also I would give credit to my or our advisors on matters topological and algebraic, Gustavo Granja and Paulo Pinto. So meanders, let me start from the picture side. Meanders are an old subject, like on this Babylonian clay tablet 1800 before Christ, which I think Carlos first saw in the Pergamon Museum, because Pergamon is in Berlin, the Pergamon Museum. And of course, you never go to the museums in your own city, so you need visitors to actually attend. Another disadvantage of Zoom meetings. And so you see in white, I have enhanced this up and down thing. These were pictures for priests or priest students to learn how to predict the future from throwing entrails like intestines of sheep or other animal sacrifice on the altar stone, and then flatten them to see how they widened. Apparently in small writing like here, you find instructions in cuneiforms on what these things mean. Unfortunately, this is the only tablet I have seen so far, and many more are probably hiding in some museums. A little later, Carl Friedrich Gauss drew this diagram, and he was interested in the ways a closed curve can intersect itself in the plane. And he marked the intersection points 1 and 2, and then he said, if I move along the curve like this, then I hit 1 and 1 again and 2 and 2. So 1, 1, 2, 2 is a possible sequence. And he started writing down all possibilities, and he noticed that some were excluded some possibilities. Now later, Henri Poincaré, in his study of twist maps, so he was proving Birkhoff twist map theorem, Birkhoff-Moser theorem, annulus maps. When you rotate in opposite directions, an area preserving map in an annulus, that you get at least 2 fixed points there. And here you already see a blue closed curve and a red closed curve. At least the arrow is indicated there. And Poincaré, this is from his original publication, and he has enumerated, interestingly, the intersection points. So there is the intersection point 1 here, 1. And then the next intersection point along the red arrow curve gets a 2 and a 3, and so on and so forth. We will later call this the Fusco-Rocha permutation, or the Sturm permutation. So Sturm was earlier than Poincaré, but it's related to Sturmian problems, and we will call it the Sturm permutation later on. So what is a meander? A meander consists of 2 sets of parentheses. Here on the top part, I showed you open and close parentheses over a blue horizontal line. And now I show you open and closed parentheses. Of course, admittedly, this intermediate part, where I tell you which is the closure of which opening parenthesis, is usually omitted in our notation. When they are nested, the parentheses, like in this picture, I call them a rainbow. And if I put them together, I see a closed meander, and I can number the intersection points, for example, along the red curve. And of course, you understand that this is precisely like the Poincaré picture. If you close the blue curve, or if you draw everything on a two-sphere. So this would be a closed meander, and you can also open the meander. Maybe you want to cut it here, and then you open the meander to the left like this. So there are various kinds of meanders. Let me talk about closed meanders for the moment. So what is a closed meander? I have a closed Jordan curve, and I enumerate its intersections with the horizontal line. And the only difference to the Babylonians is that I join the beginning and the end of the intestines. Now, let me briefly show you how this relates to billiards. This was work with Pablo Castañeda. I am drawing a Cartesian boundary here. So there are points, boundary points here, which are integer coordinates on the planar lattice. And then I'm shooting at 45-degree angle from a midpoint A here, and follow this curve as the arrows indicate, and point, 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 it gets reflected. And in this case, it happens to close up to a single closed curve, self-intersecting. But I can open this, and for example, this guy will be that arc, and the off-diagonal arc will be this bottom arc. And in this way, the billiards correspond to the closed meanders. And on the right side, I show you an image where not all half integer boundary points are reached, but actually we have two connected components. And here is the little red sausage on the bottom. We have two connected components of the boundary curve, as opposed to one connected of the billiard shooting curve. On the left, the billiard is transitive on the half integer points. On the right, it is not. And with such billiard methods, you can, for example, show the following. If you take a closed meander, like in the upper left, where you take a number p of nested arcs on top, of nested open closed parentheses, and a number q next to it. And on the bottom, you take what we call a rainbow, namely a single nest of p plus q stacked parentheses, p plus q open, p plus q close. Then this is a meander that is connected. This is a connected curve if and only if p and q are co-prime. And if you take three such stacks here, P, Q, and R, then this configuration is a meander if and only if P plus Q is co-prime to R plus Q, where Q is the middle one here. Such simple formulas do not extend to stacks of four meanders. And if you want to find out more about this, then I strongly recommend the very nicely illustrated book by Anna Karnauhova on Sturm Global Attractors, seaweed algebras, and so on, which also covers some of the algebraic aspects of meanders. So where are the differential equations? Nowhere yet. No differential equation inside. Instead of talking about differential equations, let me talk about Temperley-Lieb algebras. So this is the Paulo Pinto contribution, so to speak. What is a Temperley-Lieb algebra? So this comes from statistical mechanics and transfer matrices and so on, or knot theory, and lots of relations to lots of fields of mathematics. It's I think of it as a matrix algebra. And so we can add the matrices. It's an associative algebra. We can also multiply them associatively. And there are certain relations. There's a parameter here. There's a parameter tau here in this algebra. And if you square one of the multiplicative generators, then you get tau. And these generators commute if they are too far apart from each other. And if they are nearest neighbor indices, so there's E0 and E1 up to En, they satisfy a funny relation. Now, the nice thing is that you can represent these things graphically. For example, the element E2 is drawn here, or E1 in this case would be like this. So I'm taking n equals 3, and I take 4 strands, and this would be E1 here. And then when you multiply, let me show you what you do. For example, here I take the element E2, E1, E3. You just put these diagrams, these formal diagrams next to each other. And for example, if you have E1, E1, then you get something like this. And you obtain like an island in the middle. And this would be counted as an extra factor tau. So this is a rule. You contract things which do not come from the boundary. And therefore, E1 squared equals tau E1, just as requested here. So this is a formal playing game like for elementary school kids. You know, they can draw these pictures and they can contract islands, so they can do calculations in Temperley-Lieb algebras. What has this got to do with meanders, if anything? Well, that's down here. If you take a trace operation, this means you connect this diagram on the right and on the left. So you're taking the right and left boundary and opening it up downwards so that you get outside here a rainbow. And that's the bottom rainbow that I had here. Rainbow, a single nest of stacked arches, and we get a meander. So the question of connectivity in meander diagrams is the question of whether or not the trace of certain products in our Temperley-Lieb algebras is tau. So this is an algebraic question, the connectivity of these parentheses curves, because you see, if every pair of parentheses from the top and the bottom would close up, then it would be easy to enumerate meanders. We would just have Catalan numbers, you know, Catalan number on top, parentheses, Catalan numbers on the bottom, we take them squared, and we would have the number of meanders. That is not so, because connectivity is a difficult counting problem. So in that sense, I would say, because connectivity, even for pairs of parentheses, top and bottom, is such a difficult problem that I think it is fair to say that I personally do not even understand Jordan curves in the plane. So there are very elementary questions about Jordan curves in the plane, which are apparently very hard to answer. And now I will talk a little bit about the combinatorics of the problem. And I think the deepest results to date are by Piotr Zograf and his co-authors he's from St. Petersburg. And but let me proceed slowly. So there is Lando Zvonkin, who wrote a book on how to enumerate and count things, and in particular on graphs on surfaces. And I want to advertise this here as a background. But now we counted permutation numbers. That means we counted a dissipative version, open meander version of these Jordan curves intersecting a horizontal line. Given the number, which we call here equilibria, first time something dynamic is mentioned, the intersection points of the meander with the horizontal line, I call equilibria. And this is an odd number because here we study things which come from southwest and go to southeast. So we study configurations like I drew here on the left. And with 1357 equilibria, you get these numbers of configurations of open meanders. And as I said before, you can always close them. So open and closed meanders is the same counting. There's something which we call Morse, and which Matthias Wolfram calls positive meanders. They are meanders with a positive net winding. And there are fewer positive meanders than general meanders. And here, the last number is 110,000 or so. So let's see what comes up. Differential and others have counted these numbers. So here is as far as I got in his table. And he enumerated and had very nice ideas and formal ideas, physicists' ideas from quantum something or other, how the asymptotics of these Meander numbers should behave. The asymptotics of the Meander numbers is an unsolved problem to date, but he is giving lists. So this was 15 years ago, and this is the guys, he was counting the guys with a single connected component, with two connected components, like pairs of parentheses, right? And three connected components and so on. And then I said that Matthias has contributed to that. So he counted the positive meanders, which was the second column in my original table, where again I only got to here. And he has a recursive procedure, a very nice enumeration procedure of these meanders, and he can get to quite large numbers. Now, let me mention at the end, Peter Zograf, he does have asymptotics of meanders. So he presents formulas, and this is highly demanding stuff. He so this essentially is applying the ideas of the late Mariam Mirzakhani, who counted closed geodesics in hyperbolic spaces, and he is applying that, or not applying that, he is adapting that. He's the theory is different, but fundamental ideas are related. Of course, it's not at all obvious what closed meanders have got to do with closed geodesics. So the connection is rather deep. And he sorts meanders by meanders which have an arc on either side from the first to the last intersection. Like on the left, there is such an arc. On the right, neither on top nor on the bottom, there is such an arc. And then he has things which we call noses. Like these are the innermost arches of our meander, with no further arches inside. And these are in black here, and he calls them pimples, which is also not unrelated to noses, because you may have these little blisters on the nose. And then he says the guys with a rainbow, they behave like n to the 2p minus 4, and the guys without behave like n to the 2p minus 5. So the probability, if you take a random meander with large number n of intersections, or actually of arches here, then the chance to get a picture like on the right is 0, the relative chance. So typical meanders have such a maximal arc. Interesting for us. So I said this is the Manning quadratic meromorphic forms on square tile surfaces. He passes to the dual surfaces and notices that each intersection point basically belongs to a square, and then he passes to moduli spaces of meromorphic differentials there. Each of the pimple refers to a pole of his meromorphic differential and uses Mazur-Veitch volumes and so on. So this is a long story, which I mean, Piotr Zograf explained this to me for a couple hours, and this is really tough for me. Okay, very deep results. It just got published this year. And one of his co-authors, Vincent Delacroix, he specified special meanders which have just nests next to each other. And the first number, which you can probably not even read here, it's 2,1, the first number counts the number of stacks on the top, and the second counts the number of stacks on the bottom. And for example, the first column, because refers to two on top, two stacks on top and one on bottom. And we already know that this requires PQ to be 1. So this is where the Euler phi function comes in. The number of integers co-prime to n, less than n, positive integers. And that's the first column and the second and so on. And he has really extensive tables of this. So these are special meanders with, you might say, given numbers of pimples or stacks on the top and on the bottom. So much for counting. Now let me start at least with ordinary differential equations, although I am told that this is a PDE seminar, so I should eventually come to partial differential equations. But the ordinary differential equation is the poor man's partial differential equation, right? You consider solutions which are independent of the second variable in these equations.
No, this is analysis and differential equations seminar, not PDE. Differential.
Oh, okay. But analysis as opposed to combinatorics, but including complex analysis, like we just had with the meromorphic quadratic differentials, right? Now, for the pendulum ODE, like for the forced pendulum, Jim York, a long time ago, pointed out chaotic dynamics in these colorful pictures where you plot in the VVX plane a Poincare section under periodic excitation. And since we are in PDE, I call the time variable x to make it an ordinary differential equation. And the colors indicate that eventually the pendulum is right rotating or left rotating or what have you. And this is the intermingled basins of attractions that you see there. Now, if you think of a boundary value problem, because we not only want to talk about ordinary, but also partial differential equations of several kinds of differential equations, if you like, then we have to impose Neumann boundary conditions. And there is a shooting method to solve the boundary value problem, which says start at x equals 0 at the left boundary. X is to the front in this picture. Start with a horizontal axis, with a v-axis, v sub x equals 0. So you have satisfied the Neumann boundary conditions. Take all those solutions, watch them evolve under this chaotic flow. You see the time x equals 1 could be very, very large, in fact. 1 is a large number, for example, if I write epsilon squared here in front of the vxx. And then my differential equation will start swirling and mixing this horizontal line around, like when you are putting milk, a little bit of milk in tea, and you start stirring, but not too much, so that it doesn't diffuse too much. And then you get a surface of solutions, which at x equals 1 defines a curve. So let's forget about the surface and just look at this curve at the end. And this is what we call the Fusco-Rocha meander, because Giorgio Fusco and our Carlos Rocha here, the default co-author, they studied these meanders. And now you can, of course, see 1, 2, 3, 4, etc. gives you a permutation. So this is how we arrive at meander curves from the pendulum equation. And from the point of boundary orders, you see that the red curve, because it came from shooting, you see it came from the shooting, the red curve, order along the red curve is the order at x equals 0 boundary. And at x equals 1, this order here, the blue order, corresponds to x equals 1 boundary, and these orders may be different. And each intersection point of the black solid point is, of course, one solution of the Neumann boundary value problem. So this is an if and only if characterization. This is how meanders enter the question of arrangements of solutions of boundary value problems to a second order ODE. And for example, there's a question which permutations could arise there. So now, since this is a PDE, a differential equation seminar, let me also proceed to partial differential equations. So let me talk for a moment about reaction, diffusion, and advection. And so the whole thing is that now I have a time variable. So now it's a PDE seminar. And x, which was time before, becomes space, and ut equals uxx, of course, is diffusion. And the nonlinearities account for reaction depending on u, and drift terms u sub x. And if you generalize this a little bit more and you study parabolic but completely nonlinear PDEs, so partial derivative of f with respect to u sub t is positive, and with respect to u sub x it is negative, say the script f, then Filippo Lapisi initiated our quest for a Lyapunov functional. So it turns out that on the unit interval, say with Neumann boundary conditions or nonlinear Neumann boundary conditions, this equation is gradient-like. It possesses a Lyapunov function with respect to a funny metric. And previous results of this type in the quasi-linear setting were due to Zelenyak. Not quite intelligible paper, but also Hiroshi Matano, who really straightened this out in his style of perfection. So we have a variational structure, and now we can compare the partial differential equation with Neumann boundary conditions and the ordinary differential equation. And the ordinary differential equation serves as giving us equilibrium profiles. And equilibria, or critical points of the functional, of the Lyapunov functional, are very important when we try to understand the dynamics. Now, what is usually forgotten in calculus of variations is that there is a gradient flow involved in that. And this gradient flow will produce heteroclinic orbits between the critical points, or I should say it's not forgotten. I mean, in the last 20, 30 years, with Conley index and Fleur homology and such things, this has become extremely popular in the Hamiltonian systems community, but perhaps still too much restricted to that community. Their point is that they study wonderful gradient flows in situations where a gradient flow does not even exist, okay? Now we have a simpler situation. Our gradient flow exists, and it's a solution of this parabolic equation. So we want to compare parabolic and ordinary differential equations now. So when we compare this, and here the figures are all by Anna Karnauhova, we have on the one side the Sturmian partial differential equations, and on the other side, the pendulum ordinary differential equation. And of course, if we know the partial differential equation, we have a global attractor, then in particular, we can put ut equals 0. And we know the pendulum ordinary differential equation, and with a little help from our numerical friends, we can figure out what the associated meander is. But we would also like to go back. So we are not satisfied with saying, such a partial differential equation possesses a global attractor. Already Olga Ladezhenskaya knew this in the 70s, but we want to know not just it's compact, it's invariant, it consists of the global solutions over time, globally forward and backward. It allows backwards time extensions and so on. But we want to know which critical points of the functional, which equilibria are connected to each other equilibria, because the attractor consists of equilibria and heteroclinic orbits connecting the equilibria one to the other. So if this is an equilibrium V minus, and that is an equilibrium V plus of Morse indices, the left higher than the right, then by this symbol, we say that there is a heteroclinic connection between them. Now, let's remember that we have various ways now to look at the objects involved in this variational problem, in this PDE problem. We have the equilibrium profiles. An example is drawn here, and we can enumerate them 1, 2, 3, 4, 5, 6, 7 on the left boundary of my X interval and on the right boundary. So these are the equilibria. They form a braid. Okay, so far so good. But then we also have a Sturm permutation associated to that. And the Sturm permutation allows us to draw the meander, which I drew here on the left. So meander and profiles of equilibria is one-to-one relation. But we also have the global attractor, where the equilibrium profiles now are points, and the arrows are heteroclinic orbits between them. So can we pass for the meander, from the meander to the global attractor? And the answer is yes, we can. And these are all the results with Kalush-Rocha, which tell you that the only thing you have to look at is this permutation, which describes the meander. And we characterized which permutations can occur. So in particular, if you think of the chaotic picture, we have no clue what permutations happen for this particular choice of nonlinearities that Jim York studied. But we can list the permutations of all possibilities for all nonlinearities. And the second theorem says that this permutation from the meander side, so this is ODE on the left and PDE on the right, that these permutations determine which equilibria are connected by heteroclinic orbits and which are not. And moreover, equal permutation means equal, C0 orbit equivalence. And here are some examples. Here are all global attractors, and in up to 4 dimensions. This, for example, is a 4-dimensional one, enumerated by their permutations of the meanders. Because now, I mean, it's easy to enumerate the meanders, at least for a small number of intersections. You just draw them all. And then you draw the global attractors associated to that. So doing PDE global attractors has become a purely combinatorial exercise, or like drawing Jordan curves in the plane. Let me draw your attention to a funny coincidence. There are 2 completely different permutations. They are not even conjugate, which show the same attractor. And there are 2 such examples. So this puzzled us for quite a long time. And perhaps I should say that the Poincaré picture, which I showed you in the beginning, is a meander. And if you open this, like I told you before, to become a pendulum meander, it happens to be exactly equivalent to this maximal dimensional animal, which we call, for those who Ceffi Infante integer. I was too combinatorial here, just a second. Infante attractor. So this is an attractor which happens for cubic nonlinearities and was discovered many years ago. And in this picture, we have erased the attractors which cannot happen for nonlinearities f of u. So the advection part is important, or perhaps the x-dependence part is important if you want any of the crossed out attractors. Now let me get deeper into the geometry of these global attractors. These global attractors, they consist of critical points and their unstable manifolds. So the set of solutions which converge to a given equilibrium in backwards time. So perhaps there is a cell decomposition. There is a cell complex associated to that. And that thing, which is not always a cell complex, is called the Dom-Smale complex. And here I drew our favorite example of a global attractor with one of the meanders, which I showed before. And on the right, I say this is a 3-ball, and I'm plotting the center of the 3-ball, O here on the right. This is inside the thing which is shown on the right, and on the right I'm showing the sphere, the 2-sphere surface of the attractor, and I'm showing it such that the right boundary and the left boundary, this is the date boundary, 180 degrees east-west, what is it, longitude, where I have to glue this together to become a sphere. Okay, and you see here a cell complex. You see some disks, two-dimensional disks, and there are two disks on the right and one disk on the left, and so on and so forth. So there should be a complex, Sturm complex Lego. However, there is a problem. If you follow the unstable manifold of an equilibrium of a critical point downwards in the functional, then this is locally a disk, n-dimensional disk. Let's say it's a three-dimensional disk, okay? So it's a ball. Now, as you approach the boundary of this unstable manifold, that's where the target heteroclinic, the connections to the target equilibria sit. That's where the other equilibria rule at the boundary of the unstable manifold. Then this boundary can be quite complicated, as the Alexander Horn sphere homeomorphic embedding of a two-sphere into three space already shows. This cannot be extended to a homeomorphism of three spaces, the standard reference two-sphere to the Alexander Horn sphere. However, in our setting, there's a Schoenflies theorem which says that such complications do not happen. Actually, the boundary is an honest sphere, it is an embedded sphere, and you can not only use the unstable manifolds of the equilibria, E is the equilibria, to define some decomposition of this global attractor as a set, but it decomposes into a cell complex, into a finite CW complex, and actually much better, it decomposes into a regular cell complex. Regular meaning that the boundary of the cell complex itself is decomposed into cells, which are themselves disks or balls with sphere boundaries and so on and so forth, down to the one-dimensional cells, which are intervals, and their boundary, which are points. So we get a very good object if we follow the Tom Smale idea of studying variational problems by following the unstable manifolds in this type of equations. So this was a result from 2014. And therefore, we can now ask, how do we pass from the ODE meander picture, from maybe just this permutation here, how do we pass to the topological description of the Tom Smale complex, the topological dynamic description, because the cells are not just abstract cells. Abstractly, this thing is homotopy equivalent to a point, this global attractor. That's also a theorem, okay? But that doesn't tell you what it really looks like. But the cell complex, which is dynamically defined by the unstable manifold of the critical folds of the critical points of our function. So this is the Tom Smale complex, which we want to pass to. And actually, there is an even finer structure, which is a signed hemisphere complex. And this is, you see, the references get more recent. We start from the Schoenflies characterization, and then we say, yeah, you have a two-sphere, nice. But in a two-sphere, there should be an upper and a lower hemisphere, or let's say a western and an eastern hemisphere. And there should be an equator between them, well, a horizontal equator between the northern and southern hemispheres, say. Or a vertical equator between Greenwich meridian 0 and date boundary 180 degrees on our old Mother Earth. And this signed hemisphere decomposition is related to counts of sign changes. So you take an equilibrium and you take V, an equilibrium V, and you take its unstable manifold. You take the boundary. We already know by our Schoenflies theorem that this is a sphere. And the upper hemisphere is given by the unstable manifolds of those equilibria W, which V connects to, because V connects to W means we are sitting on the boundary of the unstable manifold, and which have a prescribed number Z of zeros for the difference. So we are counting the intersections between two equilibria. This intersection count is crucial this is where the one-dimensionality of our problem comes in. If you are in higher spatial dimension, then we have comparison theorems, parabolic comparison, monotonicity theorems. You start above, you stay above for two spatial profiles. And this would correspond to Z equals 0, no intersections, but in one dimension, the structure is much finer. And this much finer structure gives us the hemisphere decomposition of the boundary of any unstable manifold. So we have a signed hemisphere decomposition. This is even better than a regular cell complex, and to my knowledge, not studied in topology. Now, this in turn allows us to define what we mean by the descendants of an equilibrium. So given an equilibrium, which I call O, and I'm thinking of O like sitting somewhere here in the center of my 3-ball, and the unstable manifold in this illustration is a 3-ball. And fixing any sign sequence, I define other equilibria originating from O recursively. And I start with V0, with an index plus and minus being the equilibrium above this one in the unstable manifold and the equilibrium below. Those are unique, above everywhere in X. And the other equilibria I define recursively such that the equilibrium which I just constructed sits on the boundary of the unstable manifold of the next one. But the next one also, you understand, has to sit in one of these hemispheres. And which hemisphere I choose, I select by a sequence of plus minus signs, plus minus, dot, 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 plus minus. So for any sequence of plus minus signs, I get a sequence O, Vn minus 1, I'm on the right now, O, Vn minus 1 down to V0 of equilibria. And it turns out, because each sits in the boundary of the guy above, that there is a chain, a cascade of heteroclinic connections where the Morse index drops down by 1 pop, 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 along the sequence. Let me give an example. No, let me give a theorem first, sorry. The theorem which we proved and which just appeared says how to determine from an abstract signed Thomson-Mail complex where the meander goes. Because now I have a Thomson-Mail complex, say, and I want to determine, is it Sturm or is it not? So I need paths. I need Hamiltonian paths, right? The order on the boundary of my shooting problem of the equilibria is a Hamiltonian path through my global attractor, through the centers of each cell, through the critical point. And defining Hamiltonian paths is not such an easy problem, huh? In graph theory. So here, if the successor of a given equilibrium O has Morse index 1 less, it always has Morse index 1 more or 1 less, then it is the descendant according to this formula. It is the topmost guy, so this is the W. And in this way, the descendants define the paths of my boundary orders. Because you see, I start from the boundary orders, I can get my Thomson-Mail complex. But once I have the Thomson-Mail complex, where is the boundary order? It's a partial differential equation, and I don't know the F. I only know who connects to who. I have no nonlinearity given. But this theorem tells you how to reconstruct the boundary orders of the equilibria in this Thomson-Mail complex. So passing from PDE to ODE is not so easy. Actually, the theorems I showed you how you pass from the Sturm to who connects to who, from ODE to PDE, these theorems we proved in the 1990s up to 2000. And it took us another 20 years to pass from the partial differential equation to the ordinary differential equation order. And now this gives us the complete meander because we can simply start at the maximal dimensional cells in our Sturm global attractor. We start at the maximal dimensional cells. Then certainly any neighbors have Morse index less than these maximal dimensions, maximal unstable dimensions, maximal Morse indices. And then we get these pieces of the meander, and then we go one down and one down and one down. Here's an example. Here is a Sturmian icosahedron drawn as a Morse male cell complex, and you see the disks, and you see the one-dimensional cells, and so on and so forth, and you see 12 fat points. These are the corners of the icosahedron, or the stable critical points in our Sturmian setting. And let me just tell you, the equilibrium O is in the middle of all this sphere. And the V2, well, I don't know, but the V0, and I'm taking plus minus plus as a descendant sequence, is in the 0-dimensional boundary hemisphere. And this is here the south pole. And now I have to, yeah. So the V1 has this V0 on its boundary, on the boundary of its unstable manifold, and sits in the sigma 1 minus sphere, because I take an alternating sequence, sign sequence for the descendants here. And therefore, it is the V1 which I drew on the bottom of this diagram. And the V2 has to sit in sigma 2 plus, which is most of what you see. The boundary is the green stuff here. And the V2 sits on the bottom because it has to be a phase which contains V1 in its boundary. So this is how you construct these descendants from a signed complex. And perhaps I should mention at least that there is also another characterization, because there's a Minimax theorem behind here. In this Minimax theorem, you take among all equilibria which you connect to from O, and which have a given number k of intersections and are in the upper or lower hemisphere, you take the equilibrium closest to O or most distant at the boundary Yoda equals 0 and Yoda equals 1. And then these extremal elements of the critical elements of the hemispheres, they are exactly the descendants. But there are choices here. You can take the left boundary, Yoda equals 0, x equals 0, or x equals 1, the right boundary. Or you can take the upper hemisphere and the lower hemisphere. And these 4 choices correspond to descendants for constant sequences, plus, 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 minus, 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 or alternating sequences, plus, minus, or minus, plus, minus, plus. So 4 choices for the sequences, 4 choices of these target guys. And the closest on one side is always the most distant at the other boundary, x equals 0 versus x equals 1. So here, let me prove that my co-author Carlos Rocha is not only a co-author or a friend or so, but he is a prophet. Oh. Because this is a handwritten note, which we try to make sense of for the last 15 years or so. So in 2005, we were together at Brown University, and he has this notation, VK upper bar and VK lower bar, and it precisely describes the theorem, which now after 15 years we can finally prove. And he also proved the prophet in another way, because he said when this would appear, this is where we would have the word corona all around. Okay, so this is my proof. So it's good to listen to co-authors, even if sometimes they only say jup jup for a proof. From complexes to meanders, looking at the time, let me skip some parts of this here. Let me mention in words that there is an ultimate discretization of Sturm meanders. In fact, there is a class of discrete versions of these parabolic equations, which is called Jacobi systems, which have similar sign preservation or sign dropping properties. And any global Sturm attractor of any dimension, for example, 3, can be realized by a discretization with only 4 points, the next higher even integer. So if the dimension of the attractor is even, then this many points suffice to have a discrete ODE analog of this attractor, C0 orbit equivalent. Of course, it's not a discretization for small step sizes or anything. And if the dimension of the attractor is odd, you have to go to the next higher odd integer. I'm sorry for Pedro Girao. I will skip the no, I will not skip. So if you want to see how this relates to satisfying Einstein constraints inside black holes, you have to contact Filippo Lapisi, who has the best results on this in terms of rotational symmetry. This is a class of equations which falls into the parabolic thing, which I just said. And let me also mention that Alejandro Lopez Nieto, who is among us, has, oh, this is permanent, I think, yeah, has a way of transferring the results I told you about parabolic equations to delay differential equations. But I will leave this for the discussion. I don't know. I will clear it later. So to summarize, we went in a triangle. In a triangle where we were talking about meanders, which after a while became ordinary differential equations meanders, positive meanders. And we saw how to pass to Thom-Smale complexes. And in the end, I explained to you how to pass back from Thom-Smale complexes to the meanders. However, there are global attractor, there are signed, how should I say, there are regular cell complexes for which there does not exist any assignment of hemisphere decompositions, which leads to a meander, because whichever way you assign it, you do all this stuff that I indicated, how to do descendants, and you can draw these curves, and these curves intersect themselves. So what we are lacking is a description in terms of a Lego, if you like, of all global attractors which arise in this class, such that I can guarantee you this attractor possesses a signed hemisphere decomposition, and following the recipes, I end up with a meander, and that meander generates as its signed Thom-Smale complex the originally given complex. So there is a lot of a construction side here. And these are some of the topics I talked about, and I thank you very much for your attention and for your extensive patience with my presentation. Thank you very much.